Hi, Ben.
All right. I hope you feel loved, Ben.
He had to go. He was. Oh, okay.
I don't know why he thought that was a good idea. Neither does his dad, but whatever. On Wednesdays, he has two hard classes at the same time. All right. I believe we were roughly around
We were doing the chart. Yeah.
right there. Okay, we are right around here. Hopefully you felt okay about these because in the long run of chemistry AP stuff, this is like not hard. For a reaction to happen, we have to put energy in. That's called the activation energy. As the reaction goes forth, if it gives off energy, it's called an exothermic reaction and it ends lower. If it takes in energy, it's called an endothermic reaction and the bump ends higher. Easy enough? Okay. Okay, occasionally there is math, and pray that you'll have this. It's just reading a graph. Like I don't know, this was a bunch of years ago. They had one of these and it had like 3 math questions on it, and it was the easiest AP math question of all time because it was 35 minus 20 or something like that. All right,
That's 17, right? Oh my
he's
gosh.
ready.
For a minute, I thought you were being legit, and I was like,
No.
Bryson, don't take this test.
No. So here we go. Now we're going to get into the math parts of this because that's what we always do. All right. So a rate of reaction can be determined by monitoring the change in concentration of either reactants or products as a function of time.
Hi, Trevor.
Hi, Trevor.
Hi, Jace.
And Jace. Sorry, we forgot.
But we didn't forget about you.
Nope. Okay. So what we're going to say is that a rate, that's too fat, will be equal to the change. And we're going to call that a triangle. Have we used that yet in this class? Change is delta. And we're going to say that that's over the change in time. When you take calculus, that'll look really familiar because it's called an interval or the derivative. So this can be defined in either the disappearance of A or the appearance of B. So if you would look here, the rate of this reaction could be defined as your final, which is 0.54 mole A, minus your initial, which was 1. And that would be divided by your change in time, which is 20 seconds. So the rate with definition according to A would be a negative value, right? And that's normal. So the rate would be equal to negative 0.46 over 20. Oh, I don't know what that is. 0.02 something? What? 0.023? Sounds right. All right, and that would be moles per second. Oh, negative, sorry, I didn't put the negative sign. We okay with that? All right. So B, yeah, right. So B would be equal, and it's not always, this would be with a 1-to-1 ratio, but it's fine. Here we will have our final, which is 0.46, minus our initial, which is 0. So it's just 0.46 over the same, whoops, not 0.20, over the same change in time. So that would be a positive 0.023. So we have the rate of disappearance for our reactants and the rate of appearance for our products. Easy enough? Go ahead. No. It's only if your coefficients are the same number that they'll be the same. And that's like one of the next 2 slides, I think. All right, now, this is what I'm talking about, 3/4 signs and the copyright. That's an arrow. All right? Makes perfect sense. Yeah. True.
I need to learn to.
It would be useful for all of us if you would learn how.
I zone out.
Yeah. And then you randomly zoom in, super excited about something that usually doesn't relate. But your passion is there. That's what matters. All right. No, you're fine. I love it.
That looked like a face of love.
All right, here we go. So here's this reaction. This is called butyl chloride. It's decomposing into butanol plus hydrochloric acid. You don't need to know that, like what it is, but you'll just see. We can take the time and we just measure the concentration versus time. That's all this graph is showing you. You okay with that?
What was that? Sorry.
This is just a time versus concentration graph. What I want you to do real quick, I want you to find the rate right here. And we'll call this the interval of A. But then I want you to come down here and I want you to find the rate here. And we'll call that the interval of B. Take a minute and find those two rates if you would. Now be careful because the time is different. These can be tricky. Take a minute. All right, so we did notice, Ben and Trevor and Jace, that at the beginning of the reaction, the rate was a larger value, meaning more stuff reacted, versus later. And that will be because as a reaction goes forward, as you convert reactants to products, there are few reactants to run into each other. It decreases. We okay with that idea? So if two things happen, you are decreasing the amount of reactants and you're increasing the amount of products. So there's less of these that can run into each other, and these are in the way as well between the reactants. So you can still get collisions, they'll just be in the wrong spot. Are we okay with that? Okay, we're going to do a simple activity here in a minute. Once again, when you get a pair, just say pair. And we're just going to experiment and see how this goes. Ready? Whoops, that's the wrong one. Ready? Set. Go!
Several pairs. Bananas. Like wait for us to like all slow down.
No, just keep going. Keep going.
Just keep going. Pear. I like that one. Tripod is good.
Keep going. Keep going.
Pear. Carrot. Pear. Apple. Pear. Ooh, we haven't said a good one. Mango. Oh, there we go. Pear. This is a good object lesson.
Keep going.
Oh my gosh! Ah!
Shh. Keep going.
What's another fruit? Strawberry. Watermelon. Fruit water. Kiwi. Right in the literal bottom of the box. Open barrel, please. You can do that.
There's still more reactants, guys. We gotta do this.
Are we done?
No, we're not done yet.
I lost track of splitting this one, so if we're
Come on,
gonna have it even
Dustin,
now.
Where
we're supposed to count.
Are we done?
No, there's more down
This
here.
is getting all the last little ones out of everything that fell out. This. It's got lines.
Okay, let's call it good.
All the reactants, guys.
There's a lot of magic. That's true. Give me that. That's your awesome food. Oh, look, there's a certain pair. Okay, we're done. We're done. Brian just blew all of this. Oh, sorry. Brian just blew all of this. It just came from that direction. So there's only two. Oh, wait, there's circles here. Pair. Give me
Ow!
Great.
Fingernail. Ow!
Okay, you can leave all that crap. Head back. Well, actually, let's chuck it. Well,
We should clean you. We should not clean you. We should help you clean this. Wow, my words did not work there.
that was weird.
I'm so sorry.
I don't think I will remember where this is in a year, so just go ahead and chuck them.
So even the pink squares.
You totally see.
Totally like. Second meter, like I stopped the second meter.
No. Oh. Okay. Was it? Yeah, it was fun.
All right.
So in the crawfish.
Wrong way. Oh, I look good.
That's debatable, but okay.
Kyle and I, we both have self-confidence.
What?
We both have self-confidence. We know we look good. Okay. Whoa. Hey.
Ah! Screen within a screen. Within a screen. He's waiting at himself.
Turn the light off. Turn the light off. We can go forever.
Oh!
I thought it'd get better contrast. Okay, whatever. There we go.
No!
Sorry, kids. All right, let me shrink this down. And whoa, hey. All right, so these are my tally marks that I made on the desk as we moved along. Holy cow, this is the worst resizing job ever.
Oh, that was between minutes.
Okay, so I did this 30-second intervals. Will you find the rate for each interval? You'll live. I didn't have time. You guys were yelling pear, Coke, and the apple. Free Shavaka, dude.
17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 38, 39. There's 53 in the first one.
Okay.
1, 2, 3, 4, 5, 6, 7, 8,
And this was 30-second intervals.
27 in the second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. The third one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the fourth one, and 1, 2, 3, 4, 5 in class.
27, I think you said. We'll give you a pass on calculating them. Should put this on Instagram. No filter. Looks so good.
Almost 15-minute video.
Your initial? 0. 0. So this would be the rate of appearance of your circle pairs. So at the start there was 0. Not very. In that first one, there's probably double that. Because the problem is you would all say pair like the same time. And I could hear you and the girls, and that was really it for the first 15, 30 seconds. But from here on, I was very accurate because it slowed down. All right. So what you just experienced is the same thing a chemical reaction will experience, in that at first, when the concentration or the amount of the little circles was high, it was pretty easy to find them and make pairs. So what was our rate for this first set? 53/30ths? Is that what we said? Was it 53? All right, so was that 0.8 something? 0.9? Oh yeah, 53/30. 1 point what? All right, so that'd be just per second. It's not moles or anything. We could like put pairs or whatever, but who cares? What was our next one? About half that, probably. And then this one was. And then this one. And this one. Whoops. So we definitely saw a decrease as the amount of reactant started to decrease, right? One way, this is like, I didn't even know there was white ones in there. It didn't really matter, but we had the circles and the big squares. One way to speed this up would have to have no pairs, right? The pink things, I mean, the squares, right? So that's an example of if we can make the mixture more homogeneous, the reaction will happen faster. If we just got rid of that was in the way, we would have had pretty much the same rate the entire time, because you just had to grab two, right? So that's another illustration of this example. But what you need to know is that the reaction rate slows down significantly over time because the concentration of reactants goes down. Now, when this happens, we could graph this, and it won't be great, but we had like, what was it? 1.7. I'm just going to put it right here. I'll just put it on. So 1.7, and then about half, and then it was about here, and then about there, or something like that. Are we okay with that? I guess it went down to 0.16. So we essentially had this right here. Are we okay with that? All right. Typically in chemistry, we only care about the instantaneous rate towards the very beginning of the reaction. So we would define the overall rate of this reaction by finding a line tangent to this curve at whatever time you were asked. So if it said at like 40 seconds, let's just pretend this is 40 seconds, you would come up here, and that blue mark, ironically, is right there, and then you would find the slope of a line tangent to that blue dot. Have you heard of the word tangent before yet? Am I still recording? Okay, good. A tangent line, if you didn't raise your hand, a tangent line is typically based on a circle. Whoops. So you have a circle, and a tangent line is a line that touches the circle in one specific point. All right. And you can find the tangent at any point that you want. You can find the slope of that tangent, and that will give us useful information. All right. In chemistry, the slope of the tangent line. Thank you. I did that myself, right in front of your eyes. Here we go. We'll finish it up. There you go. Oh, that's not a tangent. I super failed right there. All right. This slope of the tangent line will give us the rate at a specific time. Okay. You'll do this in calculus a lot. Are you in calculus? Have you found rates and crap? Right. This is just the same idea. Are you okay with that? We rarely define the rate by what happens at the end, because we don't care. What really we care about is when there's high concentrations of stuff, how fast does this reaction happen? Easy enough? Thank you for permission to move on. All right, so the average rate of this reaction over each interval is the change in concentration divided by the change in time. So it's dx over dt. Essentially, x would be the thing you're testing. All right, note that the average rate decreases as the reaction proceeds. This is because as the reaction goes forward, there are fewer collisions between reactant molecules. Right? You guys were simulating the collisions by finding the pairs. All right? And as the amount of circles decreased, it became harder to find the pairs. That worked a lot better than I thought it would. All right, easy peasy lemon squeezy. All right, now, as the reaction goes forward, the concentration of reactants goes down, the concentration of products goes up. We've said that. All right, and then this is just talking about what exactly what I just said. A plot of concentration versus time for this reaction yields a curve like this. All right, I've already got the tangents drawn, but the red line would be your curve. All right, the slope of a line tangent to the curve at any point is the instantaneous rate at that time. You okay with that? Now, why I told you you would need a nice calculator for this unit is sometimes you're asked to find the tangent. And you can do that math. You can do it, rise over run, find your slope that way. But we're going to have to plot these lines in a calculator, and then we just push a button, and it will tell me the slope of the tangent line at any point in time. You can just trace your curve, and it will tell you. So it's nice to have that option. Uh-oh, what happened? Oh, I hate this thing. Hold on.
Some interesting content for
Oh my Hades. Fine. This thing has a timer option. It's like for professional presenters, which is probably nice. It vibrates when your time's over, but it also stops working when your time's over. And I don't even need to use it. I just bump it once in a while, and then it shuts off, and then I have to reset it. Yep. All right, now. All reactions slow down over time. Therefore, the best indicator of the rate of a reaction is the instantaneous rate near the beginning. Okay? Just make sure you're okay with that. So we go right pretty close to the start and find a tangent line, and that's how we'll define the rate of a chemical reaction. All right. Sorry, I'll go back, Brian. So this is what Hayden talked about like 10 minutes ago, and I said it's the next couple of slides. Well, it was a lot later, sorry, but we're there now. All right, so in this reaction, the ratio of your reactants to products is a 1-to-1 ratio. Thus, the rate of disappearance of one is the same as the rate of appearance of the other. But that is only true under that one specific condition, that your coefficients is the same value. All right, So what if the ratio is not 1 to 1? To me, this is the most confusing slide of the year. I don't know. To me, it's just common sense and whatever. But here we go. If you now have coefficients, you have this. It's the rate is equal to negative 1/2 the change of hi over time, which is equal to the change of I over time. Now, what that is saying, it's just showing you that one is related with the 2 and one is not. I would not write that down. I would just say this. Or in other words, the rate of I2 appearance is equal to half the rate of I2 disappearance. Like, I don't know, maybe that equation makes perfect sense to you, but it never has to my head. Like, I get it. I just like to think about it. Okay, look at this equation one more time. While we read that, I'll get them both. So what this is saying, this math in this sentence, is saying that the rate of appearance of this is equal to half the disappearance of that. Because for every 2 that disappear, 1 appears. Are we all right with that? There's 1 or 2 test questions that test this, and one of them's coming up. These are all gases. That's okay. And the only reason they really would put that is because this is an acid, but this reaction wouldn't happen if it was an acid. So it's saying these are the gas versions of hydrogen monoxide, which is kind of weird. All right. Anyway, here's the general, and this is what I really mean by it's the most confusing slide of all time. I wouldn't write that down. Personally, I have never used that in my entire life. But it's just saying you can put the coefficients in the right ways to solve for any rate of any part. So the example just was 2s plus 3O2 goes to 2SO3, and we called that A and that one B, and we came up with that, which comes up with that. Now, I just talk it out in my head that the rate of appearance of this will be 2/3 the rate of disappearance of that. All right, the rate of disappearance of that would be 3/2 as much. You just put whatever coefficient you're talking about on top, and then the second thing you compare to on bottom. That to me is easier than all that. But if you like that, it's in your book, it's in your notes, and it's right there. We'll eventually learn what we call an ICE table. And ICE stands for initial, change, and equilibrium, and it can apply to these, and then it's not that bad. All right. So here we go. This is straight from your test. I'm not even going to change a thing, and it's the easiest question on the test, so make sure you get it. So talk with your lab partner real quick. Which substance in the reaction below either appears or disappears the fastest? And ignore this vertical line. That was just where I was with my cursor when I screenshotted this. Okay, are we all okay that it is oxygen? Okay, it's a super simple question. We can rewrite this word for word. Which substance has the highest coefficient? That's the answer to this question. It's 7. It disappears at 7/4 the rate of that, at 7/4 the rate of that appearing, and 7/6 the rate of that appearing. You okay with that? All right. Then we'll just call it good. Tomorrow, please make sure you come. What we're going to teach you tomorrow and the next day is not hard unless you don't come. Because then you show up the next day and everyone's typing in their calculator all these numbers and getting answers and you're completely lost. Good? Okay, we'll pick it up. The next 2 days are 2 of my favorite days of the year. I love this idea. And like